Okay, we're going to take a look here at a couple of more examples that are referring to related rates. And I just kind of want to overemphasize, what is a related rate? A related rate is a special rate of change that is with respect to time. So when we are finding the derivative of some given quantity, that derivative is going to be represented with respect to time. So just overly emphasized. So we saw a few examples. We're going to take a look here at a few more. And we're going to get to problem number 8. Let's get to problem number 8 now. And this is the thing that I want us to kind of stick to our game plan. We want to be looking for a geometric formula. If one's given, we want to state what's given, state what we need to find, solve the problem, and then provide a conclusion. Some of these you may or may not have to draw a figure, so we just want to be mindful of that. So let's take a look here. What this is saying here is the area of a triangle with sides A and B contain an angle theta is given by A equals 1/2 AB sine theta. Here, what this is going to illustrate, if A is equal to 2, B is equal to 3 centimeters, and theta, and look at this, is increasing at a rate here of 0.2 radians per minute. How fast is the area increasing when theta is pi over 3? So there's a lot that we have. So nicely, they're giving us the formula is that A is going to equal 1/2 AB, and this is going to be sine theta. So the formula is given. State what is given. So this is going to illustrate over here that we know A is going to equal 2 centimeters. We know B is going to equal 3 centimeters. So we're stating what's given. Also, theta is increasing at a rate of 0.2 radians per minute. So what that is going to illustrate that d theta with respect to time is going to equal the 0.2 radians per minute. Those are my 3 givens. Then they ask, what are we finding? So how fast is the area increasing? So how fast is the area? So they want us to find dA with respect to time is what we are looking for. And so this is what we are finding. Now, what this is going to illustrate here is for this particular problem, for A at least, we are going to have to take the derivative with respect to time of A. Come on. And then this here is also going to illustrate that we are going to take the derivative with respect to time. And since we know that A, B are given, so when you multiply that, that's going to give you 6 divided by 3, misspoke, divided by 2, you're going to simplify this to be a 3 sine theta. And now we're taking the derivative of both sides with respect to time. So you're going to get dA dt is going to be a 3 cosine theta times d theta dt. And now you replace what you know. Now we also, I forgot to write this here, but we knew here that, well, I don't want to write that now, because you find dA dt when theta here is pi over 3. So we make that substitution at the very, very end. So we get d theta, I misspoke, dA dt is going to be 3 times cosine of pi thirds times d theta dt. And because it was increasing, notice that that value is positive, 0.2. And then again, our units here are going to slightly change. And the reason why is because we're talking about area. And so for this particular case, what is cosine of pi thirds? You're going to get 1/2 times 0.2. And when you do that calculation, this simplifies down to 0.3. So here, the area is increasing at a rate here of 0.3 area unit centimeters squared per minute. And if you think about this, right here, it's not perfect, but it'll give you an idea. We're dealing, with a triangle. And what's happening is that think of that triangle just getting bigger and bigger and bigger, is what this is in reference to. Okay, let's take a look here at another example, number 14. If a snowball melts so that its surface area decreases at a rate of 1 centimeter squared per minute, find the rate at which the diameter decreases when the diameter is 10 centimeters. So, if you, I'm not the best artist here, but, if you take, if you take a look and you're, trying to, oh God, that's horrible. How about, it's not the best drawer, so give me a second. Okay, so here it is. Copy and paste. So you have this sphere here, and what's happening as this sphere, the diameter is decreasing, then the surface area is going to decrease. So in this particular case, since we're focusing on the surface area, the geometric formula for that is, for a sphere, is S is going to equal a 4 pi r squared. That's the formula. And if the surface area is decreasing at a rate, decreasing is a negative value. So given is ds dt is going to be a negative 1 centimeters squared per minute. That's what we know when we are what's given. However, because this is the fact here that, this formula is in relationship to the radius, then in this particular case, if we let x represent the length of the diameter, right, then the diameter x here is going to equal twice the radius, which is going to imply that r is going to be x over 2. So that's going to be important in our formula here, because now what this is asking is to find the rate at which the diameter. So what they're asking us to find is dx dt. That's what they're asking us to find. So when you take s, which equals pi, 4 pi, r is going to be replaced with the 1/2 x, and you square it. What's nice is that the 4's are going to cancel. So what is this going to be is pi x squared. And now when you take the derivative with respect to time of both sides, you're going to get ds, you're going to get dt. This is going to be a 2 pi, and this is going to now be dx dt. Oh, critters, typo. Take 2. This is going to be 2 pi x, and this is going to be dx dt. And now what we're looking for here is, or finding this dx dt. So now we're going to make a substitution for ds dt, which is a -1. This is going to be 2 pi when the diameter is 10. So x is going to be replaced with 10 times dx dt. And when you solve for dx dt, you get a -1 over 20 pi is going to equal dx dt. And so what this is going to illustrate, find the rate at which the diameter decreasing. So the rate of decrease is, and because we're using the word decrease, right, we don't write the sign. So we write 1 over 20 pi, and the units in this case are going to be centimeters per minute. And again, right, I'm working our way up into some more challenging related rates. And we'll start taking a look at those next week. So, the rule of thumb is to, work the problems, right, that are assigned in the practice, because there's so many different variations of these related rates. Is what I want you to kind of start assessing and being mindful of when you're doing the practice.